January 17, 1991. Row 300 hours local time. 2 hours after Operation Desert Storm commenced. An Iraqi SA-6 gainful mobile surface-to-air missile site, positioned 15 kilometers northwest of Basra, received orders to activate their tracking radar. Coalition aircraft were penetrating Iraqi airspace in large numbers. The air defense network needed full coverage to engage the American strike packages effectively. The radar operator, a captain with 8 years' experience operating Soviet-designed systems, flipped the activation switches. The straight flush fire control radar began radiating, its beams sweeping the sky in search of targets. Within seconds, the system detected multiple contacts at various ranges and altitudes. The operator began the engagement sequence, preparing to launch SA-6 missiles at the closest threats. 80 miles to the southwest, aboard an F-4G Wild Weasel aircraft orbiting at 25,000 feet, Captain David Henderson's threat warning system lit up. A distinctive tone sounded in his helmet. The display showed the radar signature, automatically classified by the onboard computer. SA-6 gainful. Straight flush fire control radar, bearing 045 degrees, range approximately 80 miles. Henderson already had an AGM-88 HARM missile loaded on the inboard pylon. He didn't need to see the target, didn't need to overfly it, didn't need to visually confirm anything. The missile's passive radar homing seeker could detect the SA-6's emissions from his current position. He selected the HARM, designated the target based on the bearing information from his threat warning system, and pressed the launch button. The AGM-88 dropped from the pylon, its rocket motor igniting 1 second later. The missile accelerated to Mach 2, climbing briefly before turning toward the bearing where the SA-6 radar was radiating. The HARM seeker locked onto the emission, tracking it precisely. The guidance system calculated the intercept solution, adjusting the missile's trajectory continuously as it covered the 80-mile distance. At the SA-6 site, the missile warning system activated. An alarm sounded. Lights flashed on the control panel. The tactical display showed an inbound anti-radiation missile, timed to impact approximately 90 seconds. The radar operator's training took over. He reached for the shutdown switches. The doctrine was clear. Anti-radiation missiles required an active radar emission to guide on target. Shut down the radar. The missile loses its target. The site survives. He shut down the straight flush radar. The emission ceased. The operator waited, hoping the missile would lose guidance and miss the site. The HARM detected the radar shutdown immediately. But unlike earlier anti-radiation missiles that would lose guidance and miss when the radar went silent, the AGM-88 incorporated memory mode. The missile's computer stored the last known position of the radar emitter. It continued flying toward that position, maintaining the intercept course even without active guidance. 70 seconds after launch, the HARM impacted 50 meters from the straight flush radar antenna. The 145-pound WDU-21 fragmentation warhead detonated, sending thousands of steel fragments across the target area. The radar antenna suffered multiple penetrations. Control cables were severed. Electronic components were damaged. The SA-6 site was disabled, incapable of engaging targets without its fire control radar. The Iraqi air defense network received urgent reports throughout the early morning hours of January 17th. SA-6 sites engaged. SA-2 sites engaged. SA-3 sites engaged. Radar systems disabled across the country. And the warning was consistent. Any radar activation resulted in missile engagement within minutes. The order came down from Air Defense Command to all units. Keep radars off unless under direct engagement. Survival took priority over mission effectiveness. The Soviet-designed integrated air defense doctrine, refined over decades and proven in multiple conflicts, had collapsed in the first hours of Desert Storm. Iraqi operators faced an impossible dilemma. They couldn't engage coalition aircraft without activating their radars. But activating their radars meant certain engagement by American anti-radiation missiles. There was no effective solution to the problem. The AGM-88 HARM had just demonstrated why modern radar-based air defense systems faced existential challenges in high-intensity conflicts. The very sensor that made them effective had become the beacon that ensured their engagement. To understand the shock this created in the Iraqi Air Defense Force, you need to understand their confidence in Soviet-designed integrated air defense systems and the doctrine they had been trained to employ. The Soviet Union had spent decades developing one of the world's most sophisticated air defense networks, designed specifically to counter American air power. The system employed overlapping layers of surface-to-air missiles providing coverage from low to high altitude. SA-2 guideline systems engaged high-altitude targets. SA-3 GOA systems covered medium altitudes. SA-6 gainful mobile systems provided flexible coverage and accompanied ground forces. Ground-controlled intercept radar stations coordinated the network, directing both SAM systems and fighter aircraft toward threats. The doctrine was comprehensive and proven. Radar systems would maintain continuous tracking of hostile aircraft. When targets entered engagement range, SAM systems would launch missiles guided by the radar tracking data. Multiple systems could engage the same target from different angles, overwhelming defensive countermeasures. Ground controllers could vector fighters to intercept aircraft that penetrated the SAM envelope. The entire network operated as an integrated system rather than individual units, creating defense in depth that had proven effective in multiple conflicts. Iraq had imported this system wholesale during the 1970s and 1980s, purchasing Soviet equipment and adopting Soviet doctrine. By 1991, Iraq possessed one of the largest integrated air defense networks outside the Warsaw Pact. Hundreds of SAM systems provided coverage across the country. Thousands of radar-guided anti-aircraft artillery pieces filled the gaps. The network had combat experience from the Iran-Iraq War throughout the 1980s, where it successfully defended against Iranian F-4 Phantom and F-14 Tomcat strikes. The SA-6 gainful system represented a particular point of pride for Iraqi air defense forces. Unlike the older SA-2 systems that required fixed installations, the SA-6 was mobile. The straight flush fire control radar, 3 missile launchers, and support vehicles could deploy rapidly, engage targets, and relocate to new positions. This mobility, Soviet doctrine taught, provided survivability against counter-battery fire and airstrikes. An enemy couldn't target what they couldn't locate, and mobile systems relocated frequently. Iraqi operators had trained extensively on Soviet equipment under Soviet instruction. The doctrine they learned emphasized the importance of maintaining radar tracking throughout the engagement. Shutting down radar created gaps in coverage that attacking aircraft would exploit. Continuous radar operation enabled the integrated network to function as designed, with information sharing between systems and centralized threat assessment. Soviet training also addressed anti-radiation missiles, weapons designed specifically to home on radar emissions. American forces had employed these weapons in Vietnam and subsequent conflicts with mixed success. The countermeasure, according to Soviet doctrine, was straightforward. Anti-radiation missiles required an active radar emission to guide on the target. If the radar operator detected a missile launch or received warning from the network, shutting down the radar would defeat the missile. The weapon would lose guidance, miss the target, and the site would survive to resume operations after the threat passed. Iraqi confidence in this countermeasure was based on operational experience and Soviet assurances. During the Iran-Iraq War, Iranian F-4s had occasionally employed American-supplied AGM-45 Shrike anti-radiation missiles against Iraqi radar sites. The tactics Soviet doctrine prescribed had worked. Radar operators detected missile launches, shut down their systems, and the Shrikes missed their targets. The same approach, Iraqi air defense planners assumed, would work against American anti-radiation missiles in any future conflict. What Iraqi forces didn't understand was the technological leap American anti-radiation missile development had achieved between the Shrike of the 1960s and the HARM of the 1980s. The capabilities were fundamentally different, and the old countermeasures would prove not just ineffective but counterproductive. The AGM-88 high-speed anti-radiation missile represented a quantum improvement over previous American anti-radiation weapons. Development by Texas Instruments produced a system that addressed every limitation previous designs had suffered. The missile itself measured 14 feet in length and weighed 800 pounds at launch. The solid-fuel rocket motor accelerated the weapon to speeds exceeding Mach 2, with performance varying based on launch altitude and range to target. From a high-altitude launch, the HARM could engage targets more than 50 miles away, covering that distance in under 2 minutes. This range exceeded the engagement envelope of most Soviet-designed SAM systems, enabling HARM-equipped aircraft to launch from positions of relative safety. The heart of the system was the passive radar homing seeker. Unlike active radar that emitted detectable signals, the HARM seeker operated silently, detecting and analyzing radar emissions from enemy systems. The seeker could identify different radar types by their signal characteristics, frequency, pulse repetition rate, and scan patterns. The onboard computer stored data on dozens of Soviet and other radar systems, automatically classifying detected emissions and prioritizing threats based on their danger to friendly aircraft. The launch modes provided tactical flexibility. In pre-briefed mode, pilots programmed known SAM site locations before takeoff. If those sites activated their radars during the mission, the HARM could engage them immediately. In target of opportunity mode, the pilot detected a radar emission during flight, identified it as hostile, and launched the HARM to engage it. The missile would home on the emission autonomously, requiring no further input from the launch aircraft. Self-protect mode enabled automatic launch when the aircraft's threat warning system detected an imminent SAM engagement, essentially allowing the HARM to function as a defensive countermeasure. The revolutionary capability that distinguished HARM from all previous anti-radiation missiles was memory mode. If the targeted radar shut down after missile launch but before impact, the HARM didn't lose guidance and miss. Instead, the guidance computer stored the last known position of the radar emitter. The missile continued flying toward that position, maintaining its intercept course based on inertial navigation. When the missile reached the target area, it would detonate, engaging the site even though the radar was no longer active. This capability completely defeated the traditional countermeasure Soviet doctrine prescribed. Shutting down the radar after detecting a HARM launch wouldn't save the site. The missile would continue to the radar's last known location. The blast radius of the 145-pound warhead was sufficient to damage or disable radar equipment, antenna arrays, control vehicles, and associated systems within a significant area. Even if the radar survived the initial engagement, the psychological impact on the operators was devastating. The countermeasure they had been trained to employ didn't work. The warhead design optimized for the anti-radar mission. The WDU-21 fragmentation warhead created thousands of high-velocity steel fragments designed to penetrate and disable electronic equipment. Radar antennas, with their delicate construction and precise alignment requirements, were particularly vulnerable to fragmentation damage. Even relatively minor damage could render the system inoperative or degrade its performance sufficiently to make it ineffective for engagement operations. Multiple aircraft types could employ the HARM, providing widespread deployment capability. The F-4G Wild Weasel, a specialized variant of the Phantom designed specifically for the suppression of enemy air defenses mission, carried up to 4 HARMs plus electronic warfare equipment. F-16C, fighting Falcons equipped with the HARM targeting system pod, could carry 2 HARMs while maintaining air-to-air and air-to-ground capability. F-A-18 Hornets employed HARMs in the strike fighter role. EA-6B Prowler electronic warfare aircraft carried HARMs to complement their jamming capabilities. This cross-platform compatibility meant that virtually any strike package could include HARM shooters without requiring dedicated specialized aircraft. The missile became operational in 1985, replacing the earlier AGM-45 Shrike and AGM-78 Standard Arm. The unit cost was approximately $280,000 per missile. Expensive but justified by the capability provided. By 1991, production had reached sufficient levels to stockpile 4,000 missiles for Desert Storm operations. ensuring adequate inventory for intensive operations. The advantages over predecessor weapons were substantial. The Shrike had limited range, requiring aircraft to penetrate close to the target and exposing them to defensive fire. The Shrike's seeker would lose guidance if the radar shut down, causing the missile to miss. The standard arm had better range, but suffered similar guidance limitations. Neither weapon could engage a radar that shut down after launch. The HARM's combination of extended range, higher speed, sophisticated seeker, and memory mode capability solved all these limitations simultaneously. When Operation Desert Storm planning commenced in late 1990, HARM received priority attention. The coalition faced the prospect of operating against one of the world's most dense integrated air defense networks. Neutralizing that network was essential to enabling strike operations against strategic targets throughout Iraq. HARM would be the primary weapon for the suppression of enemy air defenses mission. The deployment for Desert Storm included more than 200 aircraft capable of employing HARM missiles. 4,000 missiles were positioned in theater, representing the largest stockpile of anti-radiation weapons ever assembled for a single campaign. The planning emphasized early and aggressive seed operations to paralyze the Iraqi air defense network in the opening hours of the war. H-hour, the commencement of air operations, occurred at 0300 hours on January 17, 1991. F-4G Wild Weasels accompanied the first strike packages penetrating Iraqi airspace. Their mission was simple but critical: launch HARMs at any Iraqi radar that activated, suppressing the air defense network and enabling strike aircraft to reach their targets unopposed. The opening minutes of the air campaign saw dozens of HARM launches. Iraqi radar operators, following Doctrine, activated their systems to engage the coalition aircraft they detected. F-4G crews detected these radar emissions immediately and launched HARMs in response. The missiles covered the distances to their targets in under 2 minutes, engaging sites before Iraqi operators could react effectively. One engagement early on the morning of January 17th typified the pattern. An SA-2 site near Baghdad activated its fan-song fire control radar, attempting to engage a strike package approaching the city. 3 F-4G Wild Weasels detected the emission from different positions. All 3 launched HARMs within seconds of each other. The first missile reached the site in 90 seconds. The radar operator detected the launch warning and shut down his system. The HARM's memory mode continued the intercept, impacting within 50 meters of the radar position. The second and third HARMs arrived within the next 30 seconds, engaging the same target area. The SA-2 site was disabled before it could launch a single missile at coalition aircraft. Iraqi air defense commanders recognized the problem immediately. Their operators couldn't defend against aircraft without activating radars, but activating radars resulted in HARM engagements within minutes. The survival rate of sites that operated their radars aggressively was effectively 0 during the first 24 hours of the campaign. The order came down through the Iraqi Air Defense Command structure quickly. Preserve the force. Keep radars off, except in extremis. Survival took priority over engaging coalition aircraft. This represented a fundamental abandonment of Soviet doctrine and the integrated air defense concept. Individual site commanders were essentially told to choose survival over mission effectiveness. The result was predictable. Iraqi air defense coverage collapsed. With radars shut down, the SAM systems couldn't engage aircraft. The integrated network couldn't function without radar data to share between sites. Ground-controlled intercept stations couldn't vector fighters without tracking information. Coalition aircraft operated with near impunity, striking targets throughout Iraq while the air defense network remained silent, paralyzed by fear of HARM engagement. Some Iraqi operators attempted to adapt tactically. SA-6 units practiced shoot-and-scoot procedures. They would activate radar briefly, achieve a quick lock on a target, launch missiles, and shut down immediately before relocating to a new position. The theory was sound. Minimize radar on time to reduce exposure to HARM. Launch missiles to at least threaten coalition aircraft. Relocate to avoid follow-up strikes. In practice, this approach achieved limited success. The brief radar activations still allowed HARM-equipped aircraft to detect the emissions and launch missiles. The time required to relocate SA-6 systems, approximately 20 to 30 minutes including breakdown, movement, and setup at a new location, wasn't sufficient to escape the engagement area before HARMs arrived. Some sites survived by never operating at all, essentially removing themselves from the battle. Those that attempted to engage faced high probability of being hit. The psychological effect extended beyond the immediate tactical problem. Iraqi air defense personnel knew that any radar activation invited engagement from weapons they couldn't effectively counter. The stress of operating under these conditions was immense. Operators knew they were exposing themselves and their crews to potential engagement every time they activated their systems. The courage required to continue operating despite this knowledge should be acknowledged, even as the ineffectiveness of their efforts is noted. Post-campaign intelligence from captured Iraqi air defense personnel confirmed the psychological impact. Multiple interrogations reported similar stories. Operators received explicit orders: do not activate radar unless under direct, immediate engagement. Some commanders told their crews that survival was more important than attempting to engage coalition aircraft. Better to preserve the equipment and personnel for future use than to lose both in futile resistance against overwhelming technological advantage. Coalition forces fired more than 2,000 HARMs during the Desert Storm air campaign. The effectiveness rate was estimated at 70 to 80%. Many missiles achieved direct hits on radar systems, disabling them completely. Some engaged sites that had shut down, achieving near misses that damaged equipment even without direct hits. Some missiles were defeated by decoys or false targets, Iraqi deception measures that achieved occasional success. But the overwhelming majority of HARM launches resulted in engagement of valid targets and suppression of Iraqi air defense operations. The Wild Weasel concept, dating back to the Vietnam War, proved its continued relevance. F-4G crews operated as hunter-killer teams working in coordination with strike packages. They would detect Iraqi radar emissions, engage them with HARMs, and monitor the results. If a site continued operating after the initial engagement, they would launch additional missiles. The presence of Wild Weasel aircraft with the strike packages enabled the bombers and attack aircraft to focus on their primary targets rather than defending against SAMs. Coalition forces achieved air supremacy within 24 hours of HE hour. Air supremacy, defined as the ability to conduct air operations at times and places of one's choosing without prohibitive interference from enemy forces, was essentially complete by the end of the first day. Iraqi air defenses were suppressed to the point where they posed minimal threat to coalition operations. This enabled the air campaign to proceed according to plan, striking strategic targets, interdicting Iraqi logistics, and preparing the battlefield for the eventual ground offensive. The failure of Iraqi air defenses to effectively resist coalition air operations had multiple causes, but HARM operations were central to the outcome. The fundamental vulnerability was inherent in Soviet air defense doctrine. The system required radar-guided surface-to-air missiles as the primary engagement method. Radar systems had to emit continuously to track targets and guide missiles. These emissions were detectable by enemy sensors and could be exploited by anti-radiation weapons. Soviet planners understood this vulnerability, but believed the countermeasures they had developed, primarily rapid radar shutdown when under missile engagement, would provide adequate protection. The technology gap between Soviet-era anti-radiation missiles and the American HARM was larger than Iraqi planners understood. The Soviet Kh-31 anti-radiation missile, roughly contemporary with HARM, lacked memory mode capability. If the target radar shut down, the Kh-31 would miss. Soviet doctrine assumed American missiles operated similarly. The assumption was wrong, and Iraqi operators paid the price for outdated intelligence. The range advantage HARM provided was equally critical. Soviet SA-2 and SA-3 systems had maximum engagement ranges of approximately 25 to 30 miles against aircraft. HARM could engage from beyond 50 miles when launched from altitude. This meant HARM-equipped aircraft could launch from positions outside the defensive envelope of the systems they were engaging. The Iraqi SAMs couldn't respond, couldn't threaten the launch platform, and had no effective defense against the missile once it was in flight. The mobility that Soviet doctrine emphasized as providing survivability proved inadequate. Mobile SAM systems like the SA-6 required significant time to displace from one position to another. Set up at a new location required leveling the vehicles, aligning the radar, establishing communications, and performing system checks. This process consumed 20 to 30 minutes minimum. HARM flight time from launch to impact was under 2 minutes. The mathematics didn't work. A site couldn't relocate fast enough to escape engagement once it activated radar and was detected. Training inadequacies contributed to the problem. Iraqi air defense operators had trained against the threat of anti-radiation missiles based on Soviet doctrine and Soviet understanding of missile capabilities. They had never faced an intensive arm environment where every radar activation resulted in rapid engagement from sophisticated weapons. The tactics they improvised during Desert Storm were developed under fire, without the benefit of proper training or realistic exercises. Improvised tactics rarely match the effectiveness of properly trained procedures. The strategic impact of HARM operations extended well beyond the tactical results of individual engagements. The missile demonstrated conclusively that radar-based air defense systems faced fundamental challenges against opponents possessing advanced anti-radiation weapons. The traditional solution of shutting down radar when under attack didn't work against memory mode-capable weapons. Operating radar invited engagement. Not operating radar meant inability to engage threats. The dilemma was unresolvable without fundamental changes to air defense doctrine and technology. Soviet military analysts studied the Desert Storm experience carefully. The collapse of Iraqi air defenses, equipped with Soviet weapons and trained in Soviet doctrine, against Western air power provided painful lessons. Post-Desert Storm development emphasized passive sensors, optical tracking systems, and reduced reliance on continuous radar emission. Modern Russian air defense systems incorporate frequency agility, attempting to make their radar emissions more difficult to detect and classify. Low probability of intercept radar modes reduce the signature of emissions, making detection more difficult. But the fundamental problem remains. Radar systems must emit to function, and those emissions can be detected and exploited. The AGM-88 received continuous upgrades following Desert Storm. The AGM-88E Advanced Anti-Radiation Guided Missile, the current production variant, adds GPS, INS navigation capability and a millimeter-wave radar seeker. These additions enable the missile to engage targets even if the enemy radar never activates. The GPS coordinates of a known SAM site can be programmed before launch. The missile flies to that position and uses its millimeter-wave radar to locate and engage the target. The radar shutdown countermeasure becomes completely irrelevant. The site will be engaged regardless of whether it operates or not. Modern air defense doctrine has evolved in response to the armed threat. Contemporary systems use intermittent radar operation, activating only briefly to update tracking information before shutting down. Passive sensors, including infrared search and track systems and electronic support measures receivers, provide situational awareness without radar emission. Decoys and false emitters attempt to dilute the effectiveness of arm attacks by providing multiple targets. But these are adaptations to a threat that fundamentally change the nature of air defense operations. The technological competition continues. Russian S-400 systems employ sophisticated frequency agility and low probability of intercept modes. Chinese air defense systems incorporate passive sensors and netted operations, attempting to minimize individual radar exposure. American developments continue improving arm capabilities, seeking to maintain the advantage demonstrated so decisively in Desert Storm. The competition between air defense and suppression of air defense will continue as long as radar-based systems remain relevant to military operations. January 17, 1991. Captain David Henderson watched the status display in his F-4G Wild Weasel as the HARM he had launched completed its flight. The threat warning system showed the SA-6 radar emissions cease, indicating the Iraqi operator had shut down his system. Henderson knew it wouldn't matter. The HARM's memory mode would complete the engagement regardless. 90 seconds after launch, the display showed impact. The SA-6 radar signature disappeared permanently from the threat warning display. Sight disabled. Mission accomplished. Henderson's weapons systems officer made the radio call, confirming the engagement. Strike packages inbound to targets in southern Iraq would face one less SAM threat. Similar engagements occurred dozens of times that night across Iraq, hundreds of times over the subsequent weeks. Each Iraqi radar activation resulted in HARM launch. Each launch resulted in site suppression or engagement. The integrated air defense network that Iraq had spent billions of dollars and decades building collapsed in the opening hours of the war. Soviet air defense planners had believed their doctrine was sound. Radar provided the tracking accuracy necessary for effective SAM engagement. Mobility provided survivability. Training provided the skill to operate effectively. The countermeasures they had developed against anti-radiation missiles would protect their systems from this specific threat. American technology had invalidated every one of those assumptions. Radar emission wasn't a necessary evil that enabled effective air defense. Against an opponent with advanced anti-radiation missiles, radar emission was a beacon inviting immediate engagement. The countermeasure of shutting down when threatened didn't work when missiles incorporated memory mode. Mobility was irrelevant when engagement occurred faster than relocation was possible. Iraqi air defense operators faced an unwinnable situation. They couldn't engage coalition aircraft without radar. They couldn't use radar without inviting HARM strikes. There was no solution within the constraints of the equipment and doctrine they possessed. The AGM-88 HARM had demonstrated that the balance between air offense and air defense had shifted decisively. A missile costing $280,000 could disable or suppress a SAM system worth millions. The engagement could occur at ranges where the SAM couldn't respond. The tactics that had been developed to counter earlier anti-radiation missiles didn't work. And perhaps most importantly, the psychological impact of facing a threat with no effective countermeasure paralyzed operations even beyond the actual physical damage inflicted. Soviet pilots and air defense operators believed radar was their shield, providing the tracking information necessary to engage and defeat air threats. American technology had made that radar their beacon, marking their positions for weapons that arrived at Mach 2 with devastating effectiveness. The revolution in air warfare the HARM represented continues to influence operations 35 years later. As long as radar-based air defense systems exist, anti-radiation missiles will remain the primary tool for suppressing them. And as long as anti-radiation missiles exist, air defense operators will face the same dilemma Iraqi crews encountered on January 17, 1991. Operate your radar and face engagement, or keep it silent and surrender the mission. There is still no good answer to that dilemma.